So we are now going to discuss about the inductors. I told you inductor is a coil like this. Okay, so in circuits you will see it like this. The symbol, it's bit similar to the resistor, so you can say when you are adding like series and parallel connections, you can consider them similar to resistors. So the equations will be very similar to the resistor. So inductor is again a energy storing device. So how the inductor works? So when you have an inductor, when you connect it to a voltage source, the conventional current is going like this. So from physics you should have learned that when there is a current in a coil, that will produce a magnetic field. It's Faraday's law, isn't it? So you can find the direction of the magnetic field using the right hand as well. So this current carrying coil produces a magnetic field. So that energy can be stored inside the magnetic field. So this is again a energy storing device like a capacitor. So it can be charged and discharged. Are we good? Okay, now under the DC condition, this one will be acting as, when it is fully charged, your current will be constantly flowing. So it's like a short circuited path. When it is fully charged or fully discharged, the current will be a constant. So it is like a short circuited path. So in the capacitors, what happened when it is fully charged or fully discharged? It was an open circuit. But the inductor is a short circuit. So that's one difference. Are we good? Okay. So inductor, also called a coil, choke, or reactor. It's a passive two-terminal electrical component that stored energy in a magnetic field when electric current flows through it. I told you that already. And the inductance is, you can find the inductance of an inductor using this equation. And inductance is measured in henries, like the resistance in a resistor, capacitance in a capacitor. We have the inductance in a inductor, and it is measured in the units henries. Are we good? And again, in your engineering materials, you should have learned about the inductance of materials, different materials. But this part we don't need it for electrical part. But again, it is depending on the number of turns in the coil, the length, the area, and this permeability, magnetic permeability of the core material here. So this one is a material property. So you should have learnt about it in engineering materials. As I have mentioned, we don't use this equation for any of the electrical questions. However, you should have all the subjects you are learning, they have a connection between the subjects. Okay, so the V, you can write an equation for the inductor. V is equals to L times di over dt. Again, this one is it is what we call not a constant. That's why you have a derivative here. When it is charging and discharging, the current is not the voltage here is changing, and so we have a equation like this. And if you make the I the subject in this one, like in the capacitors, you have a derivative here, integration. You can use the integration and you can make the I the subject. So if you make the I the subject, you will get an equation like this. Again, this will be in your next topic. Okay, charging and discharging part is in your first order circuits, which is next week topic, next module topic. So far, for the time being, we are not going to use any of these at this moment. We are only discussing about the DC condition, inductor in a DC condition. Are we good? Energy stored in an inductor also you can find like this. Only difference here when you compare with the capacitor is half capacitor was half times the capacitance times the V squared. Am I right? So here you have L and the I squared. So if you know the current through the inductor, you will be able to find the energy stored. Are we good? Okay. Energy is measured in joules. Okay, I told you when under the DC condition, your inductor will be a short-circuited path. So you can just draw a short-circuit path, like in the capacitor you draw it open circuit. Likewise, this one you can draw it as short-circuited path. And also the the symbol also very similar to resistor. So when they are in parallel to each other, you can consider them like this, like same as your resistors. And when they are series with each other, you can just add them in the same way. So they are like resistors. Okay, capacitors are opposite to the resistors, and you can remember it. You know the symbol is very similar to resistor, so they two are goes together, but the other one is opposite. Are we good? And also when you voltage division rule and the current division rule, it is same as your resistors. When you want to find when the two inductors are in parallel, current is coming to this node and splitting between the two inductors, and you can see to find the current across the inductor 1, you need to times the inductance opposite one. Do you remember? You did that for the resistors, didn't you? We use those equations there. So, and when you consider the voltage is equals to same inductance divided by the total. Yes. You don't get this current division rule, voltage division rule. They are not in your equation sheet. They are like, you know, they are the definitions, or else they are like theory. You need to know that it's like the basic theories. Same like the yeah. You can remember them. Inductors and resistors same, but capacitors always opposite. Okay, are we good? Any question? No question? Okay. Okay, now can I give you a few minutes for you to find the equivalent inductance of this one? I'll give you a few minutes, okay? Okay, so these 40 and 20 are in series, so when you add them together, what will happen? 60 millihenries. Okay, then this 60 and 30 are in parallel to each other. You can draw, okay? You don't skip steps, because till you get familiarized with this, don't skip steps. So this will be 60 and 30 are in parallel to each other, so that will be 30 times 60 divided by 90, so that is 20. Is that right? Okay. Now if I redraw it, so I get like this. Am I right? Is this right or wrong?
Is it only applied to this one? Like, it didn't apply for anything else?
It is applied to all the, like, you know, when you have inductors, it's like that. So when the inductors are in series, what is the equivalent inductance? They are 40 and 20 are in series with each other. When you add them together, what will happen? 60, yes. So 60 and 30. So instead of having these two, you have 60 like this, isn't it? Now 60 and 30 are in parallel. So when you add these two together, that will be 20, isn't it? Then you will come to here. Now the 120 are in series. So when you add them together, what will happen? 120. Then the 120 and 40. Yes. So you have to 120 and 40. Okay. So that 30 and 20 are in series. So that will be 50. Then the 50 and 50 are parallel. So that will be 25. isn't it? So your LEQ is 25 millihenries. Is that right? Any question?
Can we just do like leave the unit 20 and just combine 100 with 100 million?
140, how do you are saying that leaving this and combining these two?
Yes.
Are they in series or parallel? Oh, no, parallel. If they are in parallel, they should share both the start and the end points. Don't they sharing? Do they sharing it? 50 and 20 is the same thing. So you can see they have one common node, but the other node, this is the end of that. This is the end of that. Are they the same points or not? No, they are either not series. So if they are in series, they need to go like this. They are not either series or parallel. Are we good? What do we mean by parallel? So this is a very important thing. If you can't recognize whether they are in series or parallel, that will be a big problem. Tell me, what do we mean by parallel? Yes. If you have something, capacitors or inductors or resistors, whatever it is, if you have like this, what do we call them? Parallel. In case if I have something like this, no, it's not like that. Let me see. Okay, if it is like that, still these two are in parallel to each other. Do you agree? Okay, now if I say something like this, if I put something like this in between, if I put something in between here, are they in parallel now? No, isn't it? So to become parallel, both of them should have the same thing. In between these points, you can't have anything else. In this case, yes. In this case, if you have, if you have, if you see like this, if you see like, if you have something like this, yes, these two are in series with each other. Yes, this one and this one are in series. Are we good? So this one and this one, they are not either parallel or series. If they are in series, this, like, you should be able to go along it without splitting. So see, if I start here and if I go like this, can we go like, can you have to split here, isn't it? It's not on the along the same path. Even if you say these two are in series, you have to split, like, some of the current, or else it's splitting there. If you come to this node, something is splitting over here. So these are not even in series. Do you get what I mean or not? If you have something like this we call they are in series, isn't it? But in case if you have something like this in between, do they in series now? No, they are not. So it's very important to understand this. Any other questions? No? Okay, can you do these ones now? I'll give you some time for you to try and do. Find the equivalent. Now you need to carefully select which ones. Always, don't start here. Start from the end. Okay, so here, this is where you want to find it. This is the point where you need to find the LEQ. LEQ. Start from the far end. Start from the far end. Then it will be easier for you. Otherwise, you don't have to start from the far end. But I think as you have confused, as you don't know exactly how to figure out whether they are in series or parallel, I think this method is better. So start from the far end and come back to the two terminals which we need to find the equivalent inductance. Okay, so even for the capacitors, even for the resistors, do the same so that you won't go wrong. Let's see, what did you get? Okay, so if you look at the first one, these two are in parallel to each other. So that is 2. Am I right? So that 2 and 1 are in series. So that will be 3. So this 3 and 6 are in okay, so 3 and 6 are in parallel, so that it will be 2. So do you all get those? Then the 2 and 5 are in series, so the equivalent the inductance here, LEQ here is 7 henries. Do you get that? Anyone got anything else? That's 7. Okay, so that's good. Are we all good? How about the next one? What did you get for the LEQ? These two are in series, then that one will be in parallel with this one, then it is again series and parallel, so this will be 3 henries. Is that right? Next one, you can't start from the far end, the last one. So you need to first do this one, isn't it? So when you do that, that will be 2. 2 and 2 are in series, that will be 4, and 4 and 4 are in parallel, so this will be 2. Are we good? Any question? No questions. That is good. Okay, now let's see a few questions with capacitors and inductors together. Okay, I want you to try this. Okay, I will help you. You determine the VC and the IL. So we need to find the voltage across this point and the current in this branch under the DC condition. First, can you draw the DC condition? I told you when the capacitor is under the DC condition, it will be open circuit, and when the inductor under the DC condition, it is short circuit. So I'll give you time for you to first draw the circuit and think, and I will help you after you try by yourself. Okay, so how do we draw the circuit under the DC condition? So your circuit will look like this. Am I right? Is this right? Okay, so we have our inductor here, so that path is short circuited, so this will be your IL. And this one, what will happen? That is somewhere here, am I right? So this one is open circuit. So even if you draw the resistor here, it doesn't make any sense because this resistance can't have any current. Am I right? So you don't need to draw this at all because it's not functional. Okay, now can't you? Now it's like your first week topic. So you need to find the voltage, current, this IC current and the voltage here. So I'll give you a few minutes again. Did you find it already or not? The current? No? Okay, can you find it? You just need the current division rule to find IC. Just one step. Current division rule to find the IC and think what will be your VC. You need to think it. What is the current IC? IL, sorry. 6 times 4 divided by 6, which is 4 amps. Is that right? And the voltage VC? How the voltage across these 2 points? You can do in many ways. Okay. So your voltage can be this. It's the voltage. Or else you can find the voltage across these points. But both the ways you should get the same voltage. So what should be the voltage? Voltage VC is 0, because like there is no resistance along that path. So voltage is the current times the resistance, so that is 0. Am I right? If you use the other orange path, what will happen? So you have a 6 amps current and it is splitted, so 4 amps going this way, so this way is 2 amps. So you can find the voltage here, which will be 4 times 2 times 4, which is 8 volts, and also here 2 times 4 is 8 volts. So they are in opposite directions. Do you see? Do you agree with me? So it's like this. You have plus and minus like this, and here you have 8 volts, and in this way you have plus and minus and 8 volts, and here you have plus and minus, which is VC. So if you apply the KVL around this, negative 8, positive 8, 8 will cancel out, and still you get the VC as 0, isn't it? Make sense or not? Yeah. What's that? Not in series. No. We didn't take it as series. Why you are saying that? You have these ones. I didn't draw. I'm just considering one closed path. Is it clear or not? Okay. If you have any question, just ask. Are you okay? Okay. Any question? No questions? Can I move to the next question? Okay, I want you to do the same here, and I'll give you a few minutes. So in this question, you need to draw the DC circuit first and find the current across the capacitor, current across the inductor and the voltage across the capacitor. Okay, so when we draw the circuit under the DC condition, what should be the circuit? Is this what you have? Is this right? Anyone got anything else? Okay, now how do we find the current going in this way will be your I across the inductor. So you use the current division rule, am I right? So that will be 10 milliamps times 30 kilo ohms divided by 30 plus 20 kilo ohms. Kilo ohms will cancel out, isn't it? So that will be 6 milliamps. Are we good? Is it 6? Okay, 50, yes, 50. Okay. Are we good? Now, where is the voltage? Voltage is across these 2 points, am I right? So you can either do this or do this. Those or both the paths should give you the same voltage. So this one, and the current is going this way, so this is also this way. So if you find this from this side, that will be current times the resistance, which is 6 times 20, but the kilo and kilo, you need to convert the unit. So 6 times 10 to the negative 3 times 20 times 10 to the positive 3. So that will cancel out. Negative, isn't it? So 6 times 10 to the negative 3 milliamps to amps, and this 20 times 10 to the 3 for kilo ohms to ohms, and these two will cancel out. One is below, isn't it? Times by 1000 and dividing by 1000. So this will be 120 volts. If you do from the other side, tell me what is happening. So if 2 amps are going that way, this way, your current is 4 amps. 6 amps is going that way, this current will be 4 milliamps, isn't it? So this will be 4 times 30. So the voltage, you still get 120 volts. Make sense? It doesn't matter which direction you consider. If you consider this way, you still get the same voltage. If you consider this way, that again you still get the same voltage. 120 and 120. Okay, now if you want to find the energy stored in the capacitor, how do you find the energy stored in the capacitor? Energy stored in the capacitor is half times the capacitance times the V squared. Am I right? So how do you put the numbers now? Half times capacitance is 6 micro. V squared is 120 squared. So whatever the number in, you get it in joules, isn't it? So if you want to find the energy stored in the inductor, that will be half times L times I squared. These ones you don't need to remember, okay? You will get the answer. You will get the equations. So half times L is 2 millihenries, 10 to the negative 3, times the current is in milliamps, so 6 times 10 to the negative 3 to the power 2. So this will give you the power across the inductor in joules again. You will get that formula, yes. These formulas you get, this one you get, yes. Any question, or are you guys okay? These formulas will be given to you, yes. Can I move to the next question? Okay. You still doing? Are you guys still doing? Okay, yeah, you take your time and finish it, and then I will move to the next one when you finish. Let me know when you finish, okay? Okay, if you have finished the previous one, you can do this, okay? Okay, so did you draw the circuit? If you draw the circuit, this is what you have. Am I right? Is this what you have? So you have your inductor here. Am I right? One capacitor somewhere here and the other capacitor here. Is that right? Is that right or wrong? Okay, so what is the current going? So you need to find the current in this path. That will be your IL. What is the current? It's a series circuit, isn't it? 4 and 6 are in series with each other, which is 10. So tell me what the current is coming out from here. It is going like this and it is coming back to here, isn't it? Is there anywhere else that current can go? Nowhere else. So current is going in that path. So what is the current? Current is 30 divided by 10, voltage divided by the resistance, which is 3 amps. Is that right? Any question? So what is the voltage V1 and V2? V2 is the voltage in this path. So there is no resistance. Short circuit, always the voltage. If it is a short circuited path, the voltage across the short circuit will be 0 because the resistance is 0. V is equals to IR. V is equals to IR. Wherever you have resistance is 0. That means short circuited means resistance is 0. So your V2 is 0. Agree or not? How about the V1? V1 is the voltage across this path, isn't it? Or else in the other way, you can choose either way, but you need to add them algebraically voltages. So voltage here, this will be plus and minus because the current is going this way. So that will be V1 is equals to current is 3 amps times the resistance is 6. So that will be 18 volts. Do you agree with that? Any question? Any question? No questions? You all okay? All good? So your current across the L1 also it's the same current, isn't it? So that one is here. This one, it's the same current, that is also 3 amps. Okay, isn't it? Are we done? Can I move to the next part? Finished? One more question. I think this is the last one. I need to check. But can you try this one, please? So we first need to draw the DC circuit under the DC condition. So that will be like this. Is that right? Yeah, they're really easy, aren't they? So we need to find the voltage across the here. So that means the voltage here. Am I right? And the current here, this current. Is that what we need to find? Is that right or wrong? So our circuit will look like this under the DC condition. Did you get the same circuit or not? So we need to find that current and the voltage. So how do we find the current? Are we right? So current coming to this point, 4 amps coming to this point and splitting. When the current is splitted, current like to go where the resistance is less. I told you last time as well. When there is a short circuit path, more current is going in the easy path. So easy path is this, isn't it? So more current is going this way. The current division rule for the resistors are like that. Only the capacitors are different. What's that? Yes. So which we need to find this one, isn't it? We need to find this path, this current. Okay, tell me like this. Okay, if I say like this. This is my R1, this is my R2. We need to find the current in the going across the R2, not through the R1, isn't it? We need to find the current going across the R2. So current across the R2 is equals to the total current times R1 divided by R1 plus R2. Is that the equation you have? Isn't it? So the voltage should be what? Voltage across these two should be voltage VC is equals to current times the resistance. Current we found 3, resistance is 1, so that will be 3 volts. And they are asking you to find the energy stored. You can find the energy stored. You just have to use the equation. So if you are fine with that, you can do it later on. C times V squared for capacitors. VL is half times L times I squared. Okay, so you can put the numbers. This one goes here, this one goes here, and you have this these two numbers as well. Are we good? Can you find the energy stored quickly? Just substituting the right values. What do you get? What's that? For the capacitance one. What is that? 9 joules. How about the next one? 1 point something. Yes, that's right. Okay, so do we all are you guys okay? All right. One more question. Okay, I think this should be the last one, maybe. Hopefully. Okay, so under the DC condition, we draw the circuit. Is that right? So you have 3 amps here coming to this node, splitting between these two. So 2 ohms here and 4 ohms here. So the current IL is the current going this way. So that current IL is equals to what? How do we find it? 3 times 4 divided by 2 plus 4. So that will be 2 amps, right? Okay, now the next, any question? Are we good? Okay. Now we need to find the voltage across these 2 points. Am I right? Again, voltage here is 0. Am I right? VC is equals to 0. So if you want to find the energy, you can find the energy as well. They're asking the energy. So WC is equals to half times C times V squared. Anyway, this will be 0 because your V is 0. And the energy stored in the inductor will be half times L times I squared, and you can put the numbers and find it. Half times L is given to us 0.5, I is 2 squared, and that will be 0.5, isn't it? What do you get? 0? This one is 0. Why? Voltage is 0, yes, because we found the voltage is 0. And across any short-circuited path, the voltage is 0 because the resistance is 0. Oh, yes, you have 5, but is there any current going across the 5? No current. There is no voltage across the 5. 5 is not functional, so you don't need to draw the 5. You don't assume it is 0 because voltage is I times R. So when your resistance is 0, your voltage is 0. It's isn't it? It's not an assumption, it is the value. Are we good? Any question? No questions? Let me see whether we have any other questions.